All right, let's get started. Today we're going to talk about nonlinear regression. And I don't think we're going to finish both these topics now, but we'll hopefully finish at least the last of this using kernels by Tuesday. First of all, before I say that, were there any questions from last time? And I want to make one more point from last time too, but were there any general questions from last time? So we have some trickiness with that, with those alternative loss functions, right? You'll hopefully get a little bit more experience with those when the actual homework comes around. You'll get a little bit more intuition with those. But they're conceptually very simple, right? It's just a different function you're optimizing. But I think in practice that can actually make for a pretty challenging set of manipulations you have to do to actually use these things. So if there are any questions at any point, just let me know. The one point I wanted to make from last time was that I showed this little figure here, right, of temperature and hour of day. And this shows the demand in gigawatts, varying temperature and hour of day. Maybe I should have slowed this down a little bit. It's kind of moving very fast here. The point I wanted to make, though, was that just like for temperature, in all the graphs I've shown so far, I cut out I just looked at the summer months. These are different, the structure of peak demand in the summer is going to be very different from in the winter, say, for example. The structure of peak demand, actually, let me maybe go back to one of these things here. So essentially, we're saying that as the high temperature gets higher and higher, we're going to keep getting more and more demand. And that's just for summer months. And this is because the main load in summer months is air conditioning, right? So higher temperature, or a very, very big load is air conditioning. So higher temperature means you need more electricity. Now, if you extrapolated this down, right, you can imagine that it would say that, well, if you have zero temperature, then that's your high temperature, that would have a demand of 0. And that clearly is not true, right? So I'm looking intentionally only at a small subset of the data here. And really, in this next class, this current class, we'll talk about what happens when I don't cheat like that, and what does this actually look like for all the data. And I did the same, in case it's not apparent here, I did the same with hour of day. So I only looked at the hour of the day from 6 a.m. to 12 noon. And that's a range where essentially, you remember from a time before I showed a graph of demand versus hour of day. And it kind of looked like this, right? It was sort of something like came down at first, then came up. And like this range right here was 6 to 12 around, say. And so that range, we sort of have this thing approximated by a straight line, kind of. And that's why I chose those hours. This is not really a realistic setting here, because obviously we're going to have other times of the day where you have other effects. And that's really what we'll focus on today, is these are things where you can represent these functions well with a line or with a plane. And the question is, well, what happens when that is not the case anymore? A lot of functions we actually want to approximate are not straight lines. What do we do to approximate functions that look nastier than this? So that's what we're going to talk about today. And let me pull that up. Okay. All right, so let's start nonlinear regression now. So as you can imagine, that graph that I showed you before of temperature, or rather peak demand going up with high temperature, is not the whole story. The whole story is actually this. So this is now, I'm not just taking summer months anymore. I'm now looking at every single day from 2008 to 2012. This is in Pittsburgh, remember. So this is the actual demand we saw in Pittsburgh. Really all of Duquesne Light, but Duquesne Light mainly serves Pittsburgh. And you can kind of see what we were looking at before was kind of just this part here, right? And that was the range where, well, we need more demand, we need more electricity when we have higher temperatures because we have air conditioning. But as you would imagine, it's not like this just falls off to 0. At a certain point, you sort of don't use air conditioning anymore, and so that kind of that effect tails off. You don't ever use negative power, you don't ever generate power from air conditioners. And as you also might expect, in the winter months, it's kind of the opposite effect, right? I should say most heating in Pittsburgh is usually gas or I'm not sure there's any oil heating here. There was some oil heating in Boston. I'm not sure if there's much oil heating here. I don't think so. It's mainly gas. We're near a lot of gas here. So this isn't as dramatic as the summer months. It's not like we're using electricity to primarily heat homes, but there are effects like this, right? Some people have electric heaters. There's need for more lighting too when the temperature is colder. Usually means the days are shorter, so you might turn on lights more often. And so there are all these other effects that take place that actually make the peak demand increase with lower temperatures too. So this is not something you'd want to approximate with a line, right? You would not want to create a model that says, I'm going to sort of draw a line that goes straight through this thing and call that your predictive model. It's probably going to be a pretty bad machine learning model, right? I should also mention that this goes the same thing for hour of day too. So here's now we're plotting the full hours of the day, 0 to 24, and it's kind of hard to see here, but actually this graph is sort of it has both those two effects. So if you look kind of closely there, you see that kind of typical demand going up during the middle of the day. It's different, the shape of that thing, for summer and winter months. So when temperature is higher, you see it much more apparently, actually. So this side is much more apparent than the other side. But it sort of captures both these things. And what this enforces is that actually this function is not a straight line, or it's not a straight plane in either dimension, right? It's actually curved if you even look at one dimension or the other. So the question is, how are we going to represent things like this? And the fundamental point of at least this take on what I'm calling nonlinear regression, though plenty of people will call this linear regression, I should add. You'll hear both names for it. What we're going to do is we're going to use the exact same mechanisms as we used for linear regression. The math is actually no different until we get to kernels, then that gets a little bit trickier. But for standard linear regression, all we're going to do is do linear regression in nonlinear features of the data. That's the key point, right? So remember, we have this feature vector, phi of x, right? And this thing we chose before, for example, when x is one-dimensional, we just chose x1 and 1 as our feature vector. And what that was really saying is that our features just describe linear functions of the data. So these terms are both linear in the data. This one's actually just constant, and this one's linear. So we call it linear regression, and it can fit lines because the actual features themselves are linear functions of the data. What's nice about this framework, though, is that we can just as easily take nonlinear functions of the data. And that'll give us much more expressive power in actually representing these functions without a whole lot more math. In fact, the math is exactly the same. So instead of this, let's just add xi squared, I squared, as a term in our feature vector. Okay? And that's all we're going to do. We're just going to add more nonlinear functions, more nonlinear features of our data. Now, it turns out there are actually two ways to do this, two ways to make nonlinear features like this. The first way is the way we'll talk about first, which is just actually to construct them, to build them explicitly. We'll see that this is actually typically a little bit easier because we keep entirely the same framework as we use for linear regression. So that's kind of nice. But what we'll see is that, especially as the dimensionality of our data gets big, this explicit construction can take a long time, just computationally. It can actually be very computationally intensive to construct features like this explicitly. Sort of actually write out what every term is. Just the size of these things gets very, very big. And this is going to lead us to a second way of dealing with nonlinearity in our predictors. And this is through a method called kernels. And kernels are a very cool technique. They've been kind of a hot topic in machine learning for 15, 20 years now probably, though they predate that by quite a bit. And what these are going to do is these are actually going to address this computational problem of really, really big feature vectors. And they're going to do it by actually using feature vectors that are very, very big without actually ever constructing them. So you just create them implicitly. This is really tricky sort of to wrap your mind around at first. But I'll show you how that works. And it's really, really cool. It's a really cool trick because you actually can work in very high dimensional feature spaces, and sometimes actually even in infinite dimensional feature spaces, which you could never represent on a computer, right? And you can do this computationally efficiently. So that's sort of very surprising, but it's a really cool trick. So first, though, let's talk about these explicit feature vectors and how we can construct these things just in the most natural way, which is just build a bigger feature vector that has more nonlinear features. So let's look at the same problem. I'm going to now build I'm going to use linear regression for the algorithm. So the algorithm is exactly the same, right? We just formed this matrix phi, which has, you remember, phi of x1 on the first row, all the way up to phi xm on the last row. And then I'm going to set theta star to be equal to phi transpose phi inverse phi transpose y. The only difference here is that now phi, as its first feature, so the first row here, has terms that have x squared in them. So we take the actual input point and square all of them. And when you do this, what your actual model is recovering now is really, well, your model, remember, tells you coefficients on these things. So your model says my prediction y is going to be equal to theta 1 times phi of xi1, so that's really xi squared. I'll make this prediction on the ith example, is going to be theta 1 times xi squared plus theta 2 xi plus theta 3. So we're actually making predictions here that are a quadratic function of the data, right? And this goes also for, obviously, for higher order things too. You can have cubic features, quartic features. You can go as high dimensional as you want. And you get more representative power because you're now fitting a polynomial to the data rather than just a linear function. Or affine function, I guess. Affine functions are linear functions that have some offset. So technically, we're actually, with this, we're fitting an affine function to the data. This is what it looks like when you do this exact procedure with a degree 2 polynomial. Okay, so I'm now taking my whole data, constructing explicit feature vectors that have xi2 in there, and I'm running linear regression, and this is the resulting model I get. The way I actually get that red line, by the way, is that I take, some large number of points on the x-axis, plug them in, construct feature vectors for those, and then just see what the output, what the resulting prediction is. So this red line here plots y hat at a uniform grid along the x-axis. We can similarly do third-degree polynomials, 4-dimensional feature vectors, because we have that constant term too. And now it looks a little bit better, right? I mean, before, this was certainly better than fitting, because I don't have a line through it, but this is certainly better than fitting a straight line through it. But it's not, you might say, okay, well, it isn't, this is sort of fitting a symmetric function, right? Because these, it's not quite symmetric, but it looks, the quadratic term makes it roughly bowl-shaped. It isn't quite what the data looks like here, even in this range. This is a pretty big miss over here, for example, and it's missing on that side too. So a degree 3 polynomial now looks a little bit better, and maybe 4th degree looks a little bit better, etc. And in fact, in terms of just how well you can fit the data, you'll keep getting better and better the more degrees you have, right? You just have more expressive power. Now, there's a problem with that, which I'll talk about in a sec, but don't worry about that just for now. So here's a general case of polynomials. And I should say, I'm showing this so far in 1 dimension, but the same thing applies to 2 dimensions and higher dimensions. I actually don't have any plots of what these look like in higher dimensions. Maybe I'll put that in next time, just for next class. But for now, I'll just show what this looks like in 1 dimension, and I'll try to extrapolate what this looks like in 2 dimensions. So let's say we have 1-dimensional input here. And I'm going to use z here instead of xi just because you have to use x sub I and all this kind of stuff. I don't want to do that. I'll just use z as a general sort of input, which isn't necessarily one of the examples in our training set. It's just an input. So z is 1-dimensional. Then it's pretty obvious, right? Your polynomials of degree d go from 1 to z squared, blah, 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 all the way up to z d minus 1 and z to the d. And the dimensionality of that big vector is going to be r to the d plus 1. Okay, so that's a general formula for creating polynomial features. It's pretty simple. There isn't a lot to it, right? It's a little trickier in 2 dimensions. So let's suppose that z is two-dimensional. I'm giving the general form there. What the general formula is it says, all right, I'm going to take all products of every zi term. So now remember, now let's say that zi is an Rn. Sorry, just z is an Rn. Because I want to be able to use, now I want to be able to use the subscript to actually index into the variable. That's why I'm using z, not x sub I. So in general, if z is an Rn, then we're going to want different elements of the zi's, kind of all possible combinations of the products of these elements, where the total power of all elements is equal to, at most, d. So now let's just give an example here. Let's say z is an R2. So that means z equals just z1, z2. Remember, I'm using subscripts here to index into the variable, just for now. I typically won't use this that much, but for seeing these things, it's useful. So first of all, we can have this term, z1 to the 0, z2 to the 0. That's fine. That's a polynomial with degree less. And I'll actually, maybe I'll set d to be equal to 2 here. So this has products of these terms with total degree less than d. Of course, this is equal to 1, right? It's just not very interesting. Oh, I mean, it is interesting. You need that constant feature. You really want that. We've been including that. But that's one term. Another term would have z1 to the 0, z2 to the 1, right? And that is just equal to z2. Then there's z1 to 0, z2 squared. Remember, the total degree here is still less than or equal to 2. What are the others in this series? I want to just yell them out. What should I write next? I won't write what all these are, but what's another term here? Yeah, so there's z1. z1 squared. Right, and z1, z2. So that's sort of the important one. You have these cross terms, right? And you can imagine that as this goes higher, and in particular, as your dimension gets of your input gets bigger and bigger, you're going to have a lot of different cross terms. You need sort of all possible combinations here. And I'm just writing it like this. Basically, the set of all products raised to some powers bi, where these powers have to sum to being less than or equal to d. Now, the size, what you can show is the size of this feature vector is actually r to the n plus d choose n. We won't show that that's true, but that's just know that that's true. And for fixed, so I get this right, for fixed n and varying d, this term grows like O of n to the d. So the more dimensions we have, or rather, the higher our polynomial degree is, we're going to have a size of a feature vector that grows exponentially in the degree of our polynomial. Right? So that's sort of make you a little nervous, right? Because we want to talk about higher dimensional inputs than just 1 or 2. 1 or 2 we can kind of visualize, so I use those a lot. But typically we want to talk about things that have many, many inputs. And if we have to use n to the d terms to even construct these feature vectors, just to write them down, you might think that's getting a little bit worrisome, right? So put that on the back burner for now. It is a little worrisome, but we won't worry about it yet. We're talking about low-dimensional things right now, so it's OK. And here's what the polynomials look like, by the way. So there's two things you should have in mind. In one term, you should keep in mind kind of the fact that you can fit polynomials to the data. But the other side of your head should have sort of a view of what all the features look like. So this is plotting now the actual features themselves as x, the input here ranges from -1 to 1. Plotting on the x-axis, of the y-axis, the value of the different features. And so what we're really doing in the previous slide is we're forming some linear combination of these different nonlinear functions to give us our actual prediction. Yeah?
Why do we use a higher polynomial data? Does it reduce the loss function?
Sorry, why do we use a higher degree? Yes, it definitely does reduce the loss function, right? Because remember, our loss function measures how far away on all these points are this line is from that line. Right, so this is our prediction. The red point right here will be our prediction. You know, for 60, if our input is 60, our prediction will be that value. And you can imagine that if you summed up all of these things, right? And I'll just show this a little bit later, kind of a little bit more concretely. If you summed up all of these losses, right, the difference between this and this, what you'd find is that you have a much lower sum of losses here than you do here, say, right? Because here you have some things like that are very far away. You have some other terms that are not very nice. I mean, you have some examples here that you kind of don't fit very well. And so, kind of very intuitively, this function has a whole less loss than this function. Right? Smaller differences between the predicted value and the actual value. And that, you can measure that via squared loss, but it'll probably be true for almost any loss, at least with this difference, right? Some minor differences, you know, one squared loss would be better than some absolute loss for something else, but here, you know, pretty much any loss function is going to rate this as being better than this one. It would have to be a pretty weird loss function otherwise. All right, so here's the general form. There's one other type of function that is very common. Polynomials are one of the most common types of features. Really, you are not limited in the features you can come up with. Anything you can come up with is a valid set of features that can help you predict the output, right? And in fact, a lot of machine learning for complex domains, things like vision problems or speech recognition problems, in some sense, the challenging task is just coming up with good features. That's almost the entire challenging task, in fact. Once you have good features, then you run some simple algorithm like linear regression, and it just works well. In our case, I'm only going to talk about kind of the basic features people typically talk about when they introduce this notation of features and stuff like this. And one of them is polynomials. It's a very common way to represent nonlinear functions of your input. And the other very common one is called radial basis functions. Goes by a lot of other names too, but radial basis functions is the term I'll use, or RBFs. And what these are functions that you space around your input space that are given by the following form. In this case, the jth element of your feature vector for some input, am I writing z or x? Z there still. This term here is equal to the exponential of a negative distance between your input z and some mean mu j. So this is really the key term right here, is this mean mu j. I guess there are two key terms, but write this one first. So what this function is remember, this is the exponential of a negative distance here, right? So if z is equal to mu j, that means this thing will evaluate to 0, and exponential of 0 is 1. So it will have the value 1 when z is equal to mu j. I should be sure to write here. So here's z. I'm showing it here for one dimension, but this is a general formula for any number of dimensions. So here in general, z is an Rn, and mu j is also an Rn. Okay? So mu j are, and j goes from 1 to, what am I calling it? I guess 1 to k, because there's k different basis functions here. All right, so this is a function of z, right? It's equal to 1 when z is equal to mu j. And I should say, I'm also just typically scale it by something. This is called the bandwidth parameter. Kind of looks like a Gaussian distribution if you've seen those, but don't think of it as a Gaussian distribution because it's not normalized the way Gaussians are, but sort of similar. When z is very far away from uj, though, right, this term here is going to be very big. And so the exponential of a negative very big thing is close to 0. So essentially, we can think of this function is 1 or close to 1 when z is close to mu j, and it's 0 as you get farther away. And what I'm showing here is exactly that. So the mu's here correspond to different mu j, and these are defined, I should say, by whatever you pick as those mu j parameters. So you can pick the centers wherever you want to. There exist some heuristics for actually how you go about picking them, but you can pick them wherever you want to. And what I'm showing here is sort of an evenly spaced grid. So this is the first mu j, this is the second one, third, etc. So how many are there? 1, 2, going crazy about this color though. 1, 2, 3, 4, 5, 6, 7 total bases here. And I'm showing the evaluation of each of these bases for different points, right? So for example, this one here has its center at 0, so mu 1 equals 0 here. And very far away from that, it's 0 valued, and similar to the other ones. And this is not as obvious immediately that you can represent kind of complex nonlinear functions using this as it is with polynomials, for example. But you can do the same thing here. So effectively, think of different ways of combining these things, different terms on these things. You can get functions that are as expressive as the ones that you get from polynomials, right? These are also nonlinear functions you can combine in different ways to get interesting functions. Yeah?
Z is the input in this case.
Yes, Z is the input.
Mu is what is mu?
So mu is a set of centers that you pick. These define the RBF. You pick k of them. Remember, because we've had the definition that phi of xi is always an rk. So the jth element of phi j depends on mu j. So what you do in some sense is you pick these kind of k different centers around your data. And for points that are close, and when your input is close to that one center, it will be, that particular feature will have a high value, and the ones that are further away will have low value. Now, the question is there some sort of, automatic way of picking those mu j's? And for the polynomial, we had that. We had you just pick, you go from 1, 3, 1, 3, 2, 3, 3, etc. And there are. I mean, a standard way of doing it is to, like the most general way of doing it is just take an even grid over your space. So here what I did is that my input, say, ranges from 0 to 1. It's really, you do this when you talk about having some sort of bounded range of your inputs, but typically you have some idea about the range of inputs, right? So, and then by the way, if you don't have that, then you're probably going to make really bad predictions outside that range anyway. So, hopefully you have some notion of how your inputs are going to, what space they're going to span. So if your input ranges from 0 to 1, and I have 7 bases here, I can just pick an evenly spaced grid of 7 points. That's for dimension 1, right? If I have two-dimensional inputs, so say I have Z1 and Z2 here, then to get a uniform grid, we actually need a lot more, right? Because then I need to pick sort of an even grid in this dimension and an even grid in that dimension. And you want to kind of come up with all possible combinations of these things. And so as you can imagine, the number of things here is going to grow very quickly with the dimension. In fact, this will grow exactly like big O of d to the n, right? Because you need, as your dimension increases, you will need, sorry, as the dimension of your input grows, you'll need more and more. And d here, I should say, is the number of sort of grid points you want in each dimension. Then the number of bases here will grow like d to the n. That's kind of a standard way of creating them. Of course, you can't do that for bigger bases. For bigger input dimensions. And so you need to play other tricks, which is what we'll get to shortly. But for relatively low dimensions, you can actually do these seem to work pretty well. All right, so let's talk about two problems now with these features. These are two different problems, and people often kind of confuse these two. So it's important to know, precisely. It's important to be able to distinguish between the two different problems that come up with higher dimensional nonlinear features. So the first one is the thing I mentioned before. This is the computational problem. Remember, the size of the polynomial features, and actually, so n plus d choose d is the same as n plus d choose n. That's how combinations, how combinatorics work. And this is O of d to the n. When you think of d being fixed increasing n, it's O of n to the d if you think of n being fixed increasing d. It's the same term, but you can think of it actually as increasing exponentially in the dimension of your input. It's like for fixed degree, the number of features, polynomial features, will grow exponentially in your input dimension n, right? So fixed d is say a 5-degree polynomial. The number of features you create will grow exponentially in the size of your input n. That was a little bit more obvious, and that's not exact, but it increases of that order. That one's pretty, a little less obvious. This one, the RBS is it's very, very obvious, right? If you have, you want a uniform grid with d different slots in each dimension, and you want to sort of cover all possible combinations of dimensions, the number of features k is going to be exactly equal to d to the n. I actually didn't even need to write O of d to the n. It's exactly d to the n. Now d means something different here. Here above d means the degree of the polynomial. Here means d centers along each dimension. I'm just using the same term to emphasize that if you fix that term, these things grow exponentially in the other term. And so, as I said before, this is a big problem, right? Because we want to deal with things that have high dimensional inputs. And it becomes quickly intractable to even store these in memory, right? This is exponentially growing, the size of these things. It's hard to compute, but you can't even store these things, right? Pretty soon, if n is 20, and you want 10 features along each dimension, that's a pretty big number of features to compute. You're not going to be able to store that in memory. All right, so this seems like a problem. It's the first problem with so we have a situation where these are very powerful, these nonlinear features. They're very, very powerful. But we might have an issue of being able to even create them. The second problem, which is very different, but also equally problematic, is the representational problem. The problem here is that as you add more and more features, our functions, our prediction function, becomes extremely expressive. And you can imagine that sort of seems intuitive, right? If you have a 200th degree polynomial, that's a very, very powerful function you have at your disposal to try to fit this data. And it might be that, and I'm going to define this a little bit more formally when we talk about evaluating machine learning algorithms, but just intuitively, you can imagine that you might overfit your data. And what I mean by that is you come up with some function that works pretty well on those exact data points you picked, right, that you happen to give as input to the system, but it doesn't work very well anywhere else. And a common example is, suppose you had some function like this, with 1, 2, 3, 4, 5, 6, 7, 8 different data points. Now you can fit this OK with a quadratic, say. It looks pretty good. This is pretty much what it does, but maybe there's a little bit of error there. But with a degree 7 polynomial, so 8 total terms, because you have a constant term too, you can actually fit this exactly. And it'll look something like this. It'll look like going up and down, passing through all these things like that. And these should all pass through there. I'm not the best at drawing this. Maybe I should rearrange my points here so they actually go through. Now, in terms of our loss function, this is a great fit, right? Because this has 0 loss. We are capturing every data point exactly. That's a great thing. But you might just say intuitively, and we'll define this a little more formally when we talk about test error and training error and things like holding out some of the points to evaluate those other ones. But sort of very intuitively, what's happening here is that you are predicting very well right at those data points and very badly very close by. Right? So very close by, you have a very bad prediction. This is not what this function you would think it should look like, given kind of your intuition about what these things actually, what functions tend to look like. So this is a different problem than computational, right? This is saying even if we could, forget about the challenge of creating these things or storing them, even if we can create very high dimensional features, that might be great for fitting those exact data points we have. but it can be really bad at coming up with kind of what we could think of as a good function to approximate our data. And we can see a few examples of this in this case. So here on the top left is a 1-degree polynomial. That's just a linear fit to this peak demand versus high temperature over every day, not just the summer months. And that looks pretty bad, right? As I mentioned before, you probably don't want to fit that with a straight line. Okay. Maybe degree 2 is a little better. Maybe degree 4 is a little bit better. Here's degree 50. And actually isn't that bad here because there's so much data that it actually can do, even degree 50 actually can work okay. But as you see, sort of when you get to the edges, which were sort of some of the hardest points to approximate for these other ones, it kind of just throws away all its knowledge and just says, I'm going to fit those exactly because I have all this representational power. I'm going to use it to just fit this point exactly. And so this passes exactly to that point here, but you can probably figure this is not a great function there. Similarly here, it actually gets these 2 points exactly, gets that one and that one exact. But it's not a very good function, right? You probably don't have any reason to think that electrical demand would kind of go up, then take a sharp dip, and then go back up. It's just our data happened to be a little idiosyncrasy of our data. The same thing happens for RBFs. So if we look at RBFs, that same exact thing happens. If you have 2 RBFs, so this is 2 different of these mu values, and here I'm just picking an evenly spaced grid over the input. If you have 2 different values, it looks okay. Maybe 4 is a little better. 10, that's still looking good. RBFs are actually can be kind of nice because they have the other parameter, which is a bandwidth parameter, which actually can help you also because that can help kind of smooth things out as well. You might see that a little bit in the homework. We're not going to worry about that too much yet. But then if you go to say 50 RBFs, oh, don't worry about this lambda for now. We're coming to that. If you have 50 RBFs, then as before, you start to kind of make these wild squiggles here that, yes, they do great on that data, but they probably don't. It's probably not what the function actually looks like. Even here, right, it's probably not what the function looks like. It's making all these kind of weird dips and such that they don't correspond to anything real. They're just kind of idiosyncrasies of the precise data points we have. So I'm first going to talk about how we deal with that representational problem. Remember, we have these 2 problems, the computational one and the representational one. And we have to deal with them in different ways. So one way to deal with the representational problem, which you saw here, is just use less features, right? That's kind of an obvious thing, okay? Degree 100 polynomial is too high, use degree 5. It's a pretty obvious solution there. But there's one more, which is something you may have seen mentioned before, which is called regularization. And regularization is another way of dealing with this representational difficulty, which actually lets you keep using high-dimensional feature vectors, but just kind of penalize them in other ways. And this is the key expression here. Instead of minimize, so actually maybe before I say that, let me go back to this problem, this example here. So this is a polynomial, and these probably actually go up a lot higher than I'm showing here. But this is a polynomial that fits these 8 data points exactly. And the way it does that is by picking a very crazy function like this. Now, if you look at, remember, so this is going to be something like this. This is going to be a function that looks like y hat I equals theta 1 x1 xi at 7th plus theta 2 xi to 6 plus blah, blah, blah. If you look at this function, the way it goes about hitting these points exactly is actually to pick very big values of these things. I mean, right? So essentially, x to the 7th just looks much like x, much like x squared. If you just look at like this range from 0 to 1, they aren't that different. The way it actually gets these crazy functions is to pick very large values, and usually values that are large and they're kind of opposite. So maybe this has a sign, very large positive number, this is a very large negative number. And you combine these things in very crazy ways to get this function that passes through these things exactly. Right? Now, that's fine, but you probably don't want that. So we could fix that by just dropping out these higher order terms and enforcing that it can't have high order polynomial terms. Or we can actually do it by penalizing the parameters themselves. We can penalize large values of these thetas. And this is a technique called regularization. Okay? So remember, before, our problem was always, this is sort of our general optimization problem here. It said we minimize over theta the sum from over our m data points of the loss between the actual value and our predicted value. And this, I'll even write this a little bit. It doesn't matter which way you put it, by the way, because losses typically are symmetric, so it won't. I might write it sometimes with the yi hats first, sometimes second. This is equal to, by the way, our parameters transpose our features. So before we were minimizing that, on top of this, we're going to add a penalty, which is some value lambda. With lambda is something we pick. We can pick lambdas whatever we want, actually. And that'll actually trade off between minimizing this or minimizing that. Plus lambda times the 2 norm of our parameters. We could pick other norms there too, by the way. They have different meanings and different, they actually can lead to very different behaviors in practice too. But what we're doing conceptually is we're penalizing large values of lambda, right? Because remember, the L2 norm is just equal to, or theta, is equal to the sum from I equals 1 to k of theta I squared, right? So if the theta i's are really big, this thing will be very big. If these are all 0, it'll be 0, so we have no penalty here. But what we're doing now is we're saying, I want to talk about a little bit, minimizing loss a little bit, and then I'm also going to kind of weigh that with how big I'm going to let my parameters get. And lambda here is called a regularization parameter, and it really, if lambda is 0, we just set lambda equals 0, then it won't pay attention to this term at all, right? It'll just minimize the losses we were doing before. If we make lambda really large, though, then this thing might dominate for even reasonable size values of our parameters. And so it'll make our parameters as small as it possibly can. Not quite 0 in this case. It'll always have a little bit of value here. But you can actually come up with different losses, with different regularizers that will make it actually pick the 0 vector and just say, OK, we have some loss here. Whatever that is, let's just assume that's that. And I should. The highest possible value you can get, I should also add, is not infinity for your loss, right? Because if you pick lambda equal to 0, this is 0, no matter what norm you pick here, because the norm of 0 is always 0. And this thing is whatever you get if you predict everything else to be 0. Because theta times x, if thetas are all 0, is always going to be 0. So you kind of trade off between two extremes. The one extreme is you always predict 0, and you suffer whatever loss you suffer. And the other extreme is you just go with the normal solution you had before, and you maybe have very big weights. And again, we'll come back to this when we talk about evaluating machine learning methods. But one way to visualize this is with what's called a Pareto optimal curve. So what I'm doing in this curve is I'm plotting our cost function, j, versus the norm of theta for different values of lambda. So I'm not showing lambda here. What I'm doing is I pick lambda, I minimize this thing, and that gives me a point right here. Because the solution will have some value of this penalty here, some value of the norm of theta squared, and it'll have some value of loss, right? And if I just pick values of lambda, say, logarithmically from, you oftentimes pick it as on a logarithmic scale just because this is sort of a multiplicative scaling between these two things. So if I pick lambda to be really, really high, I get a point over here. Right, and this is actually the point where, sorry, pick lambda really, pick lambda really high, I get, no, over here, sorry, getting my dimensions confused. Pick lambda really, really high, I get this point right here. Because my optimization problem will pick theta to be essentially equal to 0. Because I'm putting so much weight on penalizing the norm of theta, that I'm going to pick some theta, namely theta equals 0, for example, that ends up over here. Right? And that achieves some loss. It's not infinite, as I said before. It's whatever loss you get when you predict everything to be 0. If I, on the other hand, pick lambda to be equal to 0, I get this point over here. Again, it's not infinite because there is some, this picks some value of theta here that has some norm. It's not 0. It's in fact, I guess in this sort of simple case, it's 10. I think I have a relatively small dimension here, so I'm not picking huge values. I'm having 20 RBFs here, so it actually picks maybe 20 is probably actually a reasonable fit. So here I have no regularization parameter, or rather it's equal to 0, and I have a resulting norm of theta over here, and I have some loss. The loss is not 0 either, right? So these points are, neither one of them actually touches the axis. There's some positive value, which sort of exemplify the extremes you can go. Either, I guess this one touches this axis, because this one is in fact 0, but this one you can't get 0 lost, even if you have, even if you don't penalize lambda at all. Sorry, don't penalize theta at all. These curves are also really useful, I should say, for identifying points that can possibly be good values of theta. So one of the things I want to kind of drill in here is, at least so far, we haven't really talked about what lambda you should really pick in practice. I've kind of said informally, you might want to trade off between the size of your parameters and the loss you experience. But your actual choice of that trade-off is kind of up to you. And in fact, it's often very domain-specific, and you can't really say beforehand what would be a good value. And what that corresponds to is that all these points on this curve are potentially optimal. They are potentially good values of theta given some trade-off between the weight of the size of theta and the loss you suffer. But if I were to give you a theta that achieved this point here, say, so it had a norm of theta to be equal to 4 and it suffered loss 1,000, well, this point is clearly not a good value of theta. It's not minimizing any combination there, right? Because for that same norm, I can find something with much lower loss, or for that same loss, I can find something with much lower norm. So this point here couldn't possibly be optimal. Every other point lies on what's called this Pareto-optimal surface, and it can actually be an optimal point for some optimization problem here. And as I say later, we'll talk a little bit more formally about how you might go about picking what the best value of lambda would be for your given task. Are there any questions about this? Because this is actually a very important figure here, and it's good to keep in mind when you think about regularization that this is what's happening here. Okay. And I should say here are some plots of, I guess this is 50 RBFs. So remember, 50 RBFs really overfits the data a lot. It's 50 RBFs with, on the top left there, lambda equal to 0. And now I'm increasing lambda. And so it's not perfect. You might think that some of the fits were better from the one before. But it's actually doing kind of the right thing, right? So if I increase lambda a little bit, ignore that kind of tailing down. It tails down like that because basically we don't have any data to the right, to the right of this point. So just look at kind of the fit in the main portion of the data itself. That's sort of the thing to keep in mind here, really. And as you can see, this first function has all these kind of bumps in it that kind of correspond to these weird idiosyncrasies of the data. This next one here, as I increase lambda, has fewer of those, and there's a lot fewer of those here. And then here we probably, on the other regime again, we're kind of like approximating it with a line or with a constant, where we're not really doing much here. We penalize the weight so much that it can't really do anything but just pick the constant function. I should say, for those that may be confused, that saw this, if you didn't see this, don't worry about it. But I'm also including that one vector in addition to these things, to the RBFs here, for example, because it has a constant term here that is not from the RBFs. It's actually from from that constant term. And I'm actually not penalizing that. I'm not putting any penalty on the last value of theta in some sense. And I'm doing that because I don't want the fact that this has, mean 2 to sort of make me be forced to predict everything down here if I have low weights. I want to predict maybe at least the mean if it has low weights. Don't worry about that if you didn't see that. Don't pay attention to that. But for those that did see it. Okay. So now in the short amount of time, actually we have some amount of time left, half an hour or so. So in the time we have left, I want to at least get started with talking about kernels. And kernels are, as I said, one of kind of the most talked about trends in machine learning in the past 15 years or so. It's been about 20 years now, actually, now that I think about it. I should probably update my slides. And this is a really, really cool idea. And there are a lot of ways of interpreting kernels. If you've taken a more mathematical course, you might see them in terms of inner product spaces and what are called Hilbert spaces. But we're not going to think about them that way here. Here we're going to think about them in a particular form. We're going to think about them as a way of using high-dimensional features without ever writing them down, ever putting them in memory. That's kind of crazy you could do that, but you can do it. And it's important, though, that kernels, from that standpoint, are about addressing those first of those problems, which is the computational problem. Remember, we had two problems. We had computationally, it's hard to even create or store things that are exponentially large. That's a big problem. And secondly, we have this representational problem, where when our function gets more expressive, we have to do things like regularize to prevent it from being too expressive. Kernels will not fix the representational problem for us. There are still representational issues with kernels. So you use these huge dimensional feature spaces without constructing them. You still have all the representational challenges inherent in that problem. You're going to need to regularize and things like that. You're going to need to address these in ways. Maybe not use too high of a degree for your polynomial and things like this. You still have to make those choices. But you can, in some sense, for free, not quite for free. There are trade-offs involved as with everything. But seemingly for free, you can work in these very high-dimensional feature spaces without ever actually constructing them. So how on earth could that work, right? That seems really, really weird. So let me show one example now of how this works. Kernel functions are, and kernels in general, are ways of evaluating. Actually, no, let me not say that first. Let me just write this down first, and then we'll get to sort of how kernels actually work. So let me take a two-dimensional input. So I'm going to have z, and I'm also going to use z prime. Sorry for that might be a little confusing because z prime will be a different input vector than z. So z and z prime here are both going to be n-dimensional vectors. And I'm going to think about a degree 2 polynomial. So d is going to be equal to 2. And in particular, I'm going to use this form of a polynomial vector. I'm actually scaling these for a technical reason. I'm scaling some of them by square root of 2. That doesn't actually change. In sort of pure linear regression, that won't change anything, right? Because you can always just pick a bigger weight on those things. If you regularize, by the way, it does change things a little bit. Because now your feature vectors are not kind of the same size. And so your size of your parameters matters. And you have to compare them on the right scale. But intuitively, at least for normal linear regression, the size of the scaling things here don't matter, right? Because you can pick whatever scaling you want. And you scale up your corresponding weights and your parameters that much more. So I'm going to write phi of z as this, in this case, 6-dimensional feature vector, which is exactly what I wrote before. It's sort of all possible polynomial terms that have degree less than or equal to 2. So you have the constant term is the first one, and you have z1, you have z2, you have z1 squared, z2 squared, and you have z1 times z2. And I'm going to go ahead and just scale these for reasons that may be obvious in hindsight, but which aren't that obvious to start off with. I'll just scale those two. I guess I wrote this kind of in the wrong order there, but it doesn't matter what order you have them in. So now let's do something, let's do the following thing. Let's take two different inputs here, z and z prime. Let's compute the inner product of these two inputs in this, in terms of the, sorry, the inner product of these two feature vectors for these two inputs. Okay? So kernels are going to be really all about inner products. And so I'm going to start by computing this inner product here. So let's just do it out. I'm going to erase this, but this one is up there. I don't want plenty of room, so it's all captured by the video. So let's take the inner product of phi of z transpose phi of z prime. Okay, using this feature representation. Well, let's just multiply each one of these out, term by term. So it's first just 1 times 1. Remember, the inner product here is just the sum of all the corresponding elements multiplied by each other. Okay, so it's 1 plus, well, the first one is just z1. We actually have a 2 there because we multiply square root of 2 by itself. So z1 times z1 prime, right? Plus 2 z2 z2 prime. Okay. Plus 2, which order do I have them in? Right. Plus, well, this next one is actually just z1 squared, z1 prime squared, plus 2 times all these things together here. That's going to be 2 z1, well, z1, z2, say z1 prime, z2 prime, plus z2 squared, z prime 2 squared. I think I got all those terms right. Okay, now let's just group terms here. And we're going to say, we'll just leave the 1 as it is. Let's group these two terms here. 2 times z1 prime, sorry, z1 prime plus z2 prime. Plus these things, and these things can be written in an interesting way. I'm going to write it as this plus this, sorry, this without the squares plus this without the squares, all squared. Because, right, we have this term squared, and then these terms times each other. So I'm writing it like this. z1 prime plus z2 prime, all squared. Everyone sees what I did there, right? Yeah?
That should be z2 prime.
I'm sure I made a little mistake here somewhere. Where is this? Where am I?
Second.
This one here?
Yes.
z2 prime, yeah.
Is it square? z2 prime square?
Oh, no. I wrote square instead of prime. That's what I did. OK. Follow the notes. I'm writing so many terms on the board, I'm going to make a mistake or two. OK, so I'm grouping these terms together, and I'm representing it as a square itself, right? But this term here, this term, is just z transpose z, right? Sorry, z transpose z prime. So I can write this as 1 plus 2 z transpose z prime plus z transpose z prime squared. And doing one more simplification, this thing is just 1 plus z transpose z prime squared. Okay, now here's the sort of the big, that's the big punchline here. I took a feature vector of dimension k here, which is 6, trying to compute inner products. But it turns out I can do that by just doing this, computing the inner product between the vectors directly. So remember, z here is an Rn. So I can compute this inner product just by an inner product of size n, right? I'll need to do my whole big inner product in dimension k. I can just do an inner product of size n. Then I take the whole thing and I square it.
Could you explain why is it Z transpose Z prime?
Why is this thing? So you mean so like this step here?
Yes.
Okay, so this step, this thing is just the definition of Z transpose Z prime. Remember, Z transpose Z prime, just by definition, is equal to, well, the sum of the corresponding elements, right? So it's you have the first element of Z, Z1, Z1 prime, plus Z2, Z2 prime. That's just the definition of inner products there. So I'm just taking these things, I'm simplifying it as that. But this is really interesting, right? Because we've expressed this great big high-dimensional inner product in terms of the low-dimensional inner product, and we just square it kind of afterwards. And this exact same math, by the way, actually I forget if I have the formal definition here. Yeah, I do. So it turns out that this is a very general statement here. We won't prove it here, but basically, if you take this thing and raise it to the d, that actually is equivalent to taking d-dimensional polynomial feature vectors. Remember, those have, if this is degree d, this would have n plus d choose d terms. That would be a lot of different terms there. But we're computing it by just computing an inner product between the two original feature vectors. So that's a big savings of space, right? Computational time and space. We're not worrying about doing this thing, we're not worrying about writing these things out. We're just going to write it like this. Compute the inner product first and erase it all to the d. And so we've really saved a ton of work here. And this is not an approximation. This is exact, right? This is exactly equal to this inner product in high dimensions, done without ever using those high dimensions. Now, I've only talked about inner products here, so you might be saying, okay, well, inner products are great. How does this actually relate to, linear regression, like we saw before? We'll get to that in a second. But first of all, just sort of drilling in how neat this is, because you really can compute very high-dimensional inner products without ever working in those high dimensions. So we're now going to use what's, so formalize this a little bit, and again, not too much, because there are much more formal ways of viewing this. So we're going to call a kernel function some function that maps from two different inputs, so from Rn by Rn to R. And a kernel function is some function that computes inner products of some feature vectors. We're actually not going to put any other restrictions on it. We're just going to use the notation of k here as these inner products of feature vectors. So basically, instead of writing this thing, which is a little bit cumbersome here, I'm just going to write k of z transpose being equal to this inner product. Now, some common kernels that you may see a lot. First one's the polynomial kernel. We just saw that. That's equivalent to inner products of these polynomial feature vectors. But again, computed very, very quickly. Then we have the RBF kernel, or called the Gaussian kernel sometimes, or squared exponential kernel. People call it all sorts of things because they don't want to call it a Gaussian kernel, even though that's what it typically goes by in literature. And that is computed in a different way. That's sort of, you can sort of think of this as like an RBF, or it's a similar formula as an RBF. But basically, to compute this kernel function, you look at the difference between these two input points, not the difference between this point and some other mean mu, like you did for an RBF. Now we're just looking at the difference between two different points. We compute this, and that's the kernel function. It turns out that this kernel function is equivalent to inner product between two RBF features, where those RBF features are infinite dimensional, and they have a mean placed at every single point in space. That's what this actually is doing in some interpretations. Right, so we're actually working with infinite dimensional features here. This thing is still equal to phi transpose phi. Those phis are these massive RBFs that actually have a center at every single point in space. So that's great. We can do inner products, high-dimensional feature spaces. How does that actually help us solve optimization problems? Now we come to something, a very nice property, which is actually really easy to show with some basic optimization theory, but I'm not going to show it. I'm just going to tell it to you, and you can use this fact. And this fact is what makes these really useful in our case. This is the following fact, which goes by the name of the representational theorem sometimes, but it has other names as well. Suppose that we are solving this problem. Minimize over theta, sum from I equals 1 to m of our loss between y, oops, not y hat, yi, and theta transpose phi xi, and then plus some regularization term. I should mention the sum here is, we're minimizing this whole thing, but in this notation the sum is only over the first bit, right? You don't include this in the sum. I mean, you could, but it would just multiply it by m. There's no reason to do that. So what the representational theorem says is something very cool. It says that the solution to this big problem here, can be represented in terms of these features and some weights. More formally, what it says is that the optimal theta is equal to some function I equals 1 to m, some alpha I. Alpha I is just some weight times phi of xi. It's actually really easy to show this using a property called duality, but I'm not going to actually show it. If anyone's curious, just come with me afterwards. I'll do it in 2 lines of math, But that's a little bit beyond kind of the rigor we're going through here today. You can just use this as a fact. This is a fact. And this is sort of very interesting now, because now we have, and I should also say, we're going to write this in terms of just alpha, or rather, yes, this is also equal to, in our old notation, or matrix notation rather, phi transpose times alpha. Remember, because phi is this big matrix here where the rows are these things, phi 1 transpose, and blah. So obviously, if you transpose this, then you'll have the columns be the different features. And so this for alpha, this term here for alpha being an m-dimensional vector is just equivalent to this actual sum here. So we'll actually typically write our theta like this. So that's the fact we're going to use, and that's what sort of makes this all possible, is the fact that we can write our solution in terms of the expansion of these things, some expansion of these things, some linear combination of them. I should also say, when m is greater than k, so we have two dimensions of interest here. So we have m and we have k, right? If k is less than m, this is obviously true. And it's obviously true because any vector can be represented as, in Rk. So for k less than m, well, you're forming some combination of m different combinations of these feature vectors. As long as they're independent, say, I guess they can't be independent because they're only k-dimensional in the pure sense. Basically, as long as these span the right dimension, maybe I won't go into that too much, but basically the point is that for k being less than m, this thing holds obviously, it holds trivially. The interesting case is when k is greater than m. So when you have a higher dimensional feature vector than terms in this sum, it's no longer obvious that your solution will actually lie in that space, right? It could lie outside that space too. But in fact, it does lie in that space for the regularized loss minimization. So this, maybe I'll just erase all this, but except for this one statement here, saying that our key statement here is that theta star equals phi transpose some alphas. That's the key result. And now this is what lets us actually use it in optimization. So let me add one more thing. If we have something like this, remember, actually maybe I'll use another way. So remember this function for least squares, for example, was written like this, right? Phi transpose theta minus y, the 2 norm of this. Sorry, 2 norm of this. And if we plug in this fact, we could also say this is somehow we're going to minimize some function like this. Theta transpose times alpha minus y. Did I not miss a slide there? I feel like I might have missed one. No. Huh. OK, anyway, what's going to happen if you do this? So you've substituted in this sort of fact into our optimization problem. And what we get is we get a lot of matrices that look like this. Phi transpose. Okay? Let's look what this actually is. What phi transpose is phi transpose is this first matrix phi, which has phi x1 transpose down to phi xm transpose times this flipped, right? So now we have phi x1 as the first column here to phi xm. So this equals something. So can anyone tell me what the first 1, element there is? What's the 1, element of this matrix? This is phi transpose. Just information multiplication, right? Yes, phi1. So it's this first row here, the inner product of this row and that column, right? So it's phi x1 transpose phi x1. Okay, then the next one, this one, is going to be now the second row, so phi x2 transpose phi x1. And in general, actually, hopefully I can get it over here if I write. All right. So in general, phi transpose ij is just going to be equal to phi xi transpose phi xj. Sorry for. These are sort of our important facts over here, but I might erase that. It's on the board. And we're going to abuse notation a little bit again, and actually just call this matrix here phi transpose. We're just going to call this thing equal to k. So sorry, we're using k to denote both the kernel function and the thing. But the important point here is, of course, this matrix contains nothing but inner products. Right? It has nothing but inner products between two elements, phi xi and phi of xj. And that was exactly what a kernel computed for us. So this matrix here, despite the fact, this is, by the way, an m by m matrix, right? Because this term here is m by k. This term is k by m. So this is an m by m matrix. That's representable. We say we're going to assume that number of data points isn't too big here. It doesn't matter how big k is. We can compute terms in this matrix just by plugging in our kernel function. So we had these huge features, these possibly infinite dimensional features, and we're representing them using just this kernel, without ever actually forming this big matrix phi here. You can just compute them using our kernel function. Now let me do one more thing, and then we'll finish up here. And I'll actually do this again next time in class, because it's worth going over twice. But this is sort of the trick here, is that we've basically taken these functions, and these are big matrices, right? But because this is equal to k, we've actually removed anything from our optimization problem that's too big. So let me start over here and go through this derivation, but I'll probably honestly do it again because it's worth going over twice. So our function, remember, that we're minimizing is j of theta. For least squares, this is going to be phi theta minus y, 2 norms squared. And we'll also add this term here, the L1 penalty. Sorry, the L2 norm penalty. We have this fact, theta equals phi transpose alpha. And now we're going to substitute this in. So this equals theta transpose, sorry, phi transpose alpha minus y, 2 squared, plus theta times phi transpose alpha squared. And now I'm going to use the fact that the 2 norm squared is just equal to, for any vector z, just equals z transpose z. I'm just going to expand these things out. Actually, first, before I do that, I'm going to first just plug in k here. So this is just going to be equal to k. So this term then, writing it out, is going to be equal to alpha transpose k transpose k. It turns out k is symmetric, actually. It doesn't matter which order you do these things in, but I'll just leave it as transposed for now. Or actually, no, I'll just erase the transpose because it doesn't really matter. Times alpha minus 2 times y transpose, I did it the same way, yeah. Y transpose alpha plus y transpose y plus lambda times, well, if you write this out, we have here alpha transpose phi transpose alpha. So this is actually, you can see k again here. So this is alpha transpose k alpha. Okay, so now this is great because we've taken this thing that has these big matrices phi, and we've gotten rid of all the matrices phi. We have just this matrix k. We don't have anything else. And now we'll take the gradient again. The gradient rules are all actually exactly the same. So the gradient of this thing with respect to alpha is this thing. We have a 2 k alpha minus, it would be k y plus 2k alpha. And this thing is gradient is equal to 0 because that's doesn't have an alpha term. We take this whole thing and we set it equal to 0. And what we get is we get the solution for alpha. Remember, you just move this, basically move this to this side, combine these terms, and also multiply through by k inverse once because you have actually every term is multiplied by k here. But what you get in the end is you get the alpha star equals k plus lambda I inverse times y. Okay, I'm going to do that very, very fast, so we'll probably go through it again. But the point here, remember, theta equals phi. Now the optimal theta equals phi transpose times alpha star. So we've effectively computed the optimal solution to this problem without ever actually forming any big matrix. We not only can represent inner products, we actually can solve optimization problems. And in the next class, I'll just sort of finish this up and show you not how you solve optimization problems, but also how you make predictions on new examples and things like this. And then I'll show some plots of what happens here. And it, as you'd expect, ends up being identically exactly equivalent to big polynomial feature vectors, just doing it without ever forming any of those. So okay, that'll be it for today. Are there any questions in the minute we have left? Okay, we'll chat next time.